welcome back to Atomic Math. Today we're going to look at specific heat capacity. And specific heat capacity of a substance is a measurement of how much energy per gram is required to raise the temperature by 1 degree Celsius. So specific heat capacity, which is given the letter C, has units of joules per gram per degree Celsius. And the higher the value, the harder it is to change the temperature. So let's just take a quick look at an example. Imagine that you place an empty iron pot on a hot burner. It's going to get hot very quickly. Now imagine the iron pot is filled with water. It's going to take a lot longer to get hot, and there are two reasons for this. The first reason, of course, is that there's a higher mass now because the pot has both water and the pot itself. But a more important thing is that the specific heat capacity of iron is 0.449 joules per gram degree Celsius, but water is 4.184 joules per gram degree Celsius. So we have to put a lot more energy to heat up the water than we do the metal. So now let's look at something specific. Let's look at thermal energy transfer. And we can use this equation here for this. And in this equation, Q is heat, M is your mass, C, of course, is your specific heat capacity, and T is your temperature. So let's look at how we could calculate an actual energy transfer with a real question. So suppose we have a piece of granite with a mass of 89.7 grams and an initial temperature of 53.6 degrees Celsius. We also have a beaker filled with 250 mils of water at an initial temperature of 18.2 degrees. Now, if we add the rock to the water, what will be the final temperature of the water and the rock when they reach equilibrium? The specific heat capacity for granite and water is 0.75 joules per gram degree Celsius and 4.184 joules per grams degree Celsius, respectively. The one thing that we're going to assume here is that this is a completely closed system. We're not going to lose any of our heat to the surroundings. We're only looking at the transfer between the rock and the water. We can say that the heat from the water is going to be the mass of the water, the specific heat of the water, and the change in temperature. And then we can say that for the granite, it's the mass of the granite, the specific heat of the granite, and the change in temperature of the granite. Now, if you notice for the change in temperature, although the initial temperatures I marked as T water and T granite, the final temperatures I just marked as T final. And that is because they are going to be the same temperature for both substances, because we've stated that we want to know what that temperature is when they're at equilibrium, meaning they are equal. So we can use the same symbol for both. And of course, we know that once they reach equilibrium, whatever heat the water has gained, the granite has lost. If we substitute into this equation, we can write it like this and say that our mass of the water, specific heat of the water, change in temperature is equal to minus mass of the granite, specific heat of the granite, and the change of temperature. Okay, let's move this up here so we can get a little bit more room. So the first thing we're going to do is distribute across our temperature change. And once we've done that, we want to take this piece right here and we're going to move it to the left-hand side. And we want to take this piece right here and move it to the right-hand side. And if we do that, we get this. So now what I'm left with is an equation where I have T final here and T final here on the same side of the equation, so now I can factor that out and leave us with this. Now, of course, I'm trying to solve for T final by itself, so I also want to get rid of everything else. So if I divide this out of both sides, I'm going to be left with an equation that looks like this. T final equals, and then everything else on the other side. So now we just come down to filling in the values that we already know. So let's look at how we would do that. So if we put our values in, we see we have the mass of the granite, the specific heat capacity of the granite, the initial temperature of the granite, and then we have the water, specific heat capacity, the initial temperature of the water, and then divided by the mass of the water, specific heat of the water, mass of the granite, specific heat of the granite. So once we've plugged all this in, we're going to get 20.3 degrees Celsius. So the final temperature that both the rock and the water will have is 20.3 degrees Celsius. Now you can see that we started with the rock at a temperature of 53.6 degrees and the water was at 18.2. So we merely raised the water just a little bit, but we changed the temperature of the rock quite a bit. And that comes down to that specific heat capacity. So as I said, the higher the value of the specific heat capacity, the more energy is going to be required to change its temperature. I personally live on the East Coast and I'm near the ocean. And the ocean works as a giant thermal mass. And because water has such a high heat capacity, it takes a long time to change its temperature. And because of this, it helps keep us a little bit more mild in the winter, but it also keeps us from getting a little too hot in the summer because this body of water is resisting the change in temperature. So that's just an example in the real world. Hopefully you found this video helpful. It was just a quick video on thermal heat transfer and heat capacity. If you like this video, go ahead and hit like. And if you want to see more videos like this, hit subscribe. And as always, if you want to see something specific, a specific question or a specific topic covered, please drop me a message in the comments. We'll see you in the next video.